Okay, here's a fine example of a science fiction. This is like one of these tawdry, ancient, overused talks that I pulled out of the vaults. It was necessary because I couldn't throw together the hydrogen talk last night that I was going to do, so I'll have to do that in the future. But this is about another kind of habitable planet, science fiction habitable planet. Now first, of course, we know about water planets. This is what we always talk about when we talk about habitable planets. It's stuck in our minds, ocean world. So this is kind of a simple image of an example of an ocean world. That's a generalized Earth. It's got water. Another kind of habitable planet is a desert planet. Now this is a science fiction planet at this point because we don't have any actual examples of it except in science fiction. And some of you have read the book Dune from 1965. If you have not, I can recommend it as one of the few science fiction novels worth reading, and it should be read. In the solar system, we have a couple of possible examples of dry planets. One, this is, by the way, is the cover of the version that I read when I was in high school. Took some searching to find that. Titan and possibly Mars are examples of land planets in our solar system. On Titan, the liquid is methane, not liquid water. On Mars, the liquid would be liquid water. Very dry there. So I guess when we're starting to talk about a fictional planet like Dune, we should talk about its facts. The known facts of this fictional planet are that Dune has powerful dust storms. There are some evaporate deposits that are reported in the course of the novel. It has a nitrogen-oxygen atmosphere. It is sparsely habitable near the poles where there is liquid water. The tropics, though, are extremely dry. There are small polar ice caps which are mined and used. There are extensive polar aquifers because that is where liquid water is. This is a habitable planet by construction of the author. And there are polar dews which are captured by people with dew catchers. If you haven't read the novel, this might be news to you. If you've read the novel, I'm just repeating things you already knew. It's a refresher. The thing about Dune is that it's a more stable planet with respect to insulation than is an aqua planet like Earth. On Earth, your tropics, at current insulations, your tropics are stabilized by heat transport to the poles. So sunlight comes in more at the tropics than at the poles. Infrared radiation is radiated more from the tropics than at the poles. But there's some of the energy is moved from the tropics towards the poles so that the poles do more of the work of radiating and less of the work, and tropics do less of the work of radiating. And so we have a little picture here of energy transport to the right. And this line across the top is the critical flux. That's the runaway greenhouse threshold. That's the point where the physics of water vapor tell you that you can no longer see the surface. You are in the runaway greenhouse regime. You will notice that locally, in the tropics, you are above that critical flux for Earth today, and this is true. If we were to elect Donald Trump and he were to build his 100-kilometer high wall around the entire Tropic of Cancer and the entire Tropic of Capricorn, you would then wall off the tropics from the poles. The tropics would then undergo a runaway greenhouse effect, which is why you have to have 100-kilometer high walls in order to keep the steam atmosphere within. And then the poles, of course, would go ice albedo, as Dorian has been talking about. Transport prevents that from happening. Now, when the aqua planet gets closer to the sun or the sun gets brighter, in our case, that's what's going to happen, the poles cannot radiate away all the heat that came from the tropics. The heat transport to the poles is no longer being able to be dealt with. The heat transport from the tropics is not dealt with as successfully at the poles, and the system runs away. And then it becomes a 1D problem because the steam atmosphere is basically a 1D atmosphere. Where land planets are different because they can radiate more efficiently from the tropics because the tropics are bone dry. Because they are dry, they can radiate at a rate higher than the runaway greenhouse threshold because it's not governed by the physics of water vapor, which is not saturated. And so a land planet can radiate more efficiently from its dry tropics, and the poles can stay habitable, and thus you can take a dry planet and put it closer to its star than you can an aqua planet. You can also imagine doing this with a synchronous rotating planet. This is an old cartoon drawn for that purpose. But you saw this in Kristen's talk this morning, this very kind of planet, where the backside is radiating, the front side is getting too much radiation, but as a whole, the thing is stable. Now in a GCM, Professor Abe did GCM simulations of a dry planet. Very, very idealized simulations of a dry planet. And what he found was that the runaway greenhouse threshold, the critical flux, I am now attempting to press a button. Not succeeding. I will walk up here and use the pointer. The critical flux for the runaway greenhouse effect for Earth used to be around 310. Now it's kind of down around 290, plus or minus 10. The threshold for complete evaporation from a dry planet, a land planet, was at 415 in these GCM simulations. So they are stable, more stable to high insulation. This is kind of a map of temperatures. On this axis here, we have the relative solar flux up to 70% above what Earth sees now, before the runaway is finally met. You will notice that the tropics are quite warm as you approach what for the dry planet, for the land planet is also a runaway greenhouse effect. At some point, the land planet does lose its liquid water at the poles, and then it does go runaway greenhouse. And that's over here. While for Earth is like more in this range. For aqua planets. Say what? This is percent, yeah. This is one of Dr. Abe's plots. I'm just cheating and using it. This is rainfall map of a dry planet, just to show you that rainfall occurs at the poles in the summer, and that's it. It's very similar to what happens with Titan, actually. So there is a better analogy to Titan. Also, dry planets have different freezing limits. They go farther from the star. Because there's not that much water, so it's harder to get an ice-albedo feedback. So the dry planet can be habitable more distant from the star. And that's what this plot shows. I don't want to go into that in any more detail, just saying that when you take a habitable zone for ocean planets, for aqua planets, it's relatively narrow. And you do the same thing for land planets, it widens up. And these are for the current Earth atmosphere. Obviously, people have been thinking about how to go further and further away from the star with potpourri of designer greenhouse gases. I think there's little doubt that you can. But moving inward with liquid water at the surface is much harder. And so the land planets can get closer. There are many basic open issues about a Dune planet because almost no research has been done. It is, after all, a science fiction planet. So one thing that hasn't been looked at all, although it's obviously important, is the stability against geochemical cycles. We have assumed a modest amount of CO2, 400 parts per million as of today, or is it 401, I think. Water is lost to chemical sinks. Could it be? Probably is. CO2 is outgassed and it subducts. Don't know. Nobody's looked at this, how long this system can remain in a stable state, or what is fixing the CO2. I mean, I'm imagining that at the poles you'll be making limestones in lakes and that you'll have marble harvesters because you'll need them for your graveyards. But I don't know how stable the planet would be to these geochemical cycles. Because we're just talking about stability right now with respect to short-term climate cycles. Atmospheric dust will clearly affect the runaway greenhouse threshold. Nobody's even put this in. You could do this with a 1D model, but nobody's done it. It's obviously going to be a dusty atmosphere. The optical depth in dust will probably be a third or a half or 1. It's not going to be small. And it's going to have a big effect on the radiative transfer in the atmosphere. And you'll probably be able to get closer to the star, thanks to the dust in the atmosphere. And then we have to define what we mean by a land planet. How do we define a land planet vis-a-vis an aqua planet? How much water is that? So we classify planets. Might as well try to classify them, right? So I have two axes here. We're going to classify insulation as the axis, the x-axis, and then the water inventory will be your y-axis. And we can have different kinds of planets. So an aqua planet Earth is in this region here. The numbers are going to be different stories we're going to tell for different kinds of planets. Europa is an example of a water planet that's on the wrong side of the iso-albedo line. So there's the ice line there. If you're to the left of the ice line, you're not habitable because you're covered with ice. Or at least not conventionally habitable because you're covered with ice. Of course, there's squids or something underneath the ice, but we can't see them. Mars is also on the wrong side of the ice line, at least I think. Question mark, I don't really know. Land planets are planets with less water. I don't know what the line is. I think it's sort of around, it's low on this plot because I think it's dry and water sinks to the bottom of your cup. So I have a low on the bottom. The moist greenhouse effect, which I'm going to talk about in a moment, occurs before you hit the runaway greenhouse. And during the moist greenhouse phase is when you can try to lose, well, you will lose hydrogen to space. And so the total inventory of water will follow curves like these green curves. So a planet blessed with a lot of water will lose some of its water during the moist greenhouse phase, but will then transition into a steam atmosphere that will be absolutely uninhabitable. A planet blessed with less water to begin with could get rid of all of its water during this moist greenhouse phase and then transition into another kind of habitable planet, a land planet. Or you could have a planet that's born without enough water in the first place. And that would be line number 4 that trucks along near the bottom of the curve. There's another picture of this, these different evolutions. You can imagine they all start off at the same surface temperature. We got 4 planets, just like Earth, with different amounts of water. Planet 1 has the most water, planet 4 is the least. And as they go through these different points, the moist greenhouse effect, you drop out number 3, and it's able to transition into a dry planet. 4 always stayed dry. Planet 2 became uninhabitable during the runaway greenhouse effect, and then transitioned into a land planet where it's habitable again in the future. And then planet 1, which is the water-rich planet, never transitions into a habitable land planet, but instead just dies out. Talk about creation myths, how to make one. And we're going to have to stop very shortly, so we will stop shortly after this picture. This is where the different thresholds are plotted on our solar system with time along the x-axis, solar luminosity, on a log scale from 0.4 to 2. Not normally done, but that's what I did. I like the way it separated the things, I guess. And the black curve here is the solar luminosity. And we're starting at about 50 million years because we don't want to go back to the earlier times when the solar luminosity is jumping all over the place. The Venus, in this story, the Venus aqua threshold is always on the wrong side. Venus was never habitable if it were an aqua planet. But had it been born a land planet, a planet without a whole lot of water, it would have initially been in the habitable zone up till about 2 to 3 billion years age. Earth is an aqua planet now, and the threshold for the runaway greenhouse is met at about 6 billion years. But if Earth were to make a transition into a land planet, say by global engineering or something, or by what I was going to show but will not show, the moist greenhouse effect, the Earth could remain habitable up till about 9.5 billion years. So another 5 billion years of habitability Earth could have if it were to transition into a land planet. But I don't think I can say more at all, except one last thing. One last thing. Oh, by the way, isn't that pretty? It's from a video game. For those of you fans of the book, Paul Atreides was born there. A key issue that I have looked at is whether Earth can make a transition to a Venus-type planet. There are several models out there that have tried to compute the properties of a moist greenhouse planet. This is a planet that's on the threshold of being a runaway. Some of them have been 1D models. I show Kaparapu models or 1D models. Casting 1988 was a 1D model. The blue curve for Abe and Matsui 1988 was a 1D model. There's also some 3D models. Wolf and Toon did a 3D model. And what they're finding is that you do get wet stratospheres as you raise the insulation. And there's a period of time, not very long, but not zero, in which the stratosphere is wet and hydrogen escape is fast. The one exception to this is a 3D model from LeConte et al., who have a model that makes an abrupt jump from a cool, temperate planet to a runaway greenhouse effect by having very high cirrus clouds. So what happens is as the stratosphere tries to get wetter in their model, it goes to high, cold cirrus clouds, which is greenhouse warming, and the thing blows up. It's a step function. And so that's also all properties of the cloud model, the microphysics model. Wolf and Thun versus LeConte et al., just modeling. As I say, models disagree. This is how long it takes to make the transition in these different models. The ocean lifetime on this axis, so you can get rid of an ocean very, very quickly if you hit one of these. And that's all to say about that. The LeConte et al. Will not, of course, make a transition. You're just dead. If they're right about how things transition when the Earth hits the runaway greenhouse, snuffed. And that will stop there with some review things, if you'd like. Another picture from a Dune paper. And that'll be all for present, because I want to answer questions if any exist. Yes, science fiction girl. You both are. Yeah. I haven't thought about it yet. And very little thought, as far as I know, only a couple papers have been done. There's been a 1 GCM paper by LeConte et al. That looked a bit at this. And then there was the Abe paper. I think that's all so far. And I don't think anyone's thought about what they look like or how they might look different from another kind of habitable planet. But I could imagine they would. Oh, yeah, it's pretty dry. Yeah. Yeah, you'd probably think it was uninhabited. Yeah. Dust. It's pretty dusty. Yeah. You may not. I don't know. Don't know. I haven't even begun to think. I mean, there's a lot to think about here because it's a different topic. Yeah, I don't think some of these things are very easy, like adding dust in a 1D model. That's not hard to do. It just hasn't been done. Yes? Yeah. Yeah. Oh, I should tell you what we think it is. Yeah. 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 Yeah.
So why do we call Earth an ocean?
We call it an aqua planet. I shouldn't use the word ocean planet. I want to use the word aqua. Yeah, that's a mistake. It's old. We tried to use words like water world, and then the astronomers came in and just shot that down. That word is used for something else. So we ended up stuck with aqua planet because nobody had used it yet.
Yeah, that's not true.
What? Somebody used aqua planet too?
Well, aqua planet in earth science means globally ocean covered.
That's what we used. Yeah, that's what we mean by it. And Earth is.
You mean Earth?
Yeah, Earth is one.
No, aqua planet means no comment.
Ah, okay. So we need to come up with another word for an Earth-like planet. But the transition from land planet to Earth-like planet will be a planet in which the poles can be isolated from the tropics.
Partially ocean covered.
Oh, no, you have to be able to isolate the poles from the tropics by energy transport. They have to be isolated. And so that would mean that you can't have oceans that are big enough at the poles that they flow into the tropics.
For a name, partially covered, is that too long?
Say what?
To say partially ocean covered, is that too long? For the name?
We were using the word aqua planet in 2005, but you already had it.
Oh, this goes back, like,
Okay, we're done for. We have to come up with yet another word. I wonder if there's a word in Japanese that we could use. Yeah, you go to another language and get a word. But basically the idea is that it's at about 100 meters of water. Global inventory is about where you get the transition from a planet that you can isolate your water at the poles to one where you can't do that. Yeah.